So we're going to have a second part to this 4.6 video because I got cut off there. I ran out of memory, and so the part 1 video got chopped off, but we're going to just pick it up where we left off. Got a little bit more to say about 4.6 before we're through. And before we go back to page 5 of the handout, let's just summarize this rank theorem again, where if A is any m by n matrix, any matrix at all, the dimension of the column space and the dimension of the row space are always equal, and we call that the rank of the matrix. The second part of that theorem is the fact that the rank of the matrix plus the dimension of the null space, the matrix, is always going to equal n, where n is the number of columns. And we were just starting to look at a couple examples of that. So if A is 3 by 5, so 3 rows, 5 columns, and I was just saying we want to think of A as a linear transformation from R5 as defining a linear transformation from R5 to R3. So from a higher dimension to a lower dimension. What we can say is, well, for one thing we can conclude is that the rank of A has to be less than or equal to 3. Less than or equal to the smaller of these two dimensions, 3 and 5. And from the equation, rank A plus dimension of null A equals n, well, if there are 5 columns, the rank plus the dimension of the null space has to equal 5. And so we can conclude something about the dimension of the null space from this. We know the rank could be 3, 2, 1, or let's see, I believe 0. And so the dimension of the null space could be 0, or I'm sorry, dimension of the null space could be 2, because 3 plus 2 would equal 5, or 2 plus 3 would equal 5, or 1 plus 4, or 1 plus 5, or 0 plus 5 would be 5. Get that out. And so what this is saying is that the dimension of the null space has to be greater than or equal to 2. Now the null space is a subspace of R5, so it certainly can't be larger than 5, because it could be the whole space. Every single vector in R5 could be sent to 0 in R3. But the null space, we know, has to be at least dimension 2, no matter what else is true about this linear transformation. So for a 3 by 5 matrix, the null space dimension has to be at least 2-dimensional. And there's another example there. I say, what if A is 9 by 4? So 9 rows, just 4 columns. So A defines a linear transformation from R4 to R9, so from a smaller dimension to a larger dimension. Now, again, we know the rank has to be, has to be less than or equal to the smaller of these two dimensions. So the rank of A has to be less than or equal to 4 in this case. And if we take our rank formula, rank A plus the dimension of the null space of A has to equal the number of columns. In this case, has to equal 4. Okay, so our rank could be 4, 3, 2, 1, 0. the dimension of the null space, in order for these to add up to 4, could be 0, 1, 2, 3, or 4. And the whole point of this example is it really doesn't tell us much of anything, because it just tells us that the dimension of the null space of A is going to be less than or equal to 4, and that, we already knew that because we're in a subspace of R4. A subspace of R4 has to be of dimension 0, 1, 2, 3, or 4. So in this case, the rank equation didn't provide any information. In the other example, the 3 by 5 example, we actually did know something about the dimension of the null space just from what the values of the rank could be and from what the rank equation told us. All right, so that really was just the little bit more about what these two examples tell us on page 5, and what they don't tell us, for example, in the second one. And we're just going to finish up here with a look back on the invertible matrix theorem. This section, this material gives us some more equivalences we can add on to the invertible matrix theorem. So remember, that only applies to square n by n matrices. It has to be square. And we have a couple more equivalences to the matrix A being invertible. If A is invertible, the column space of A is Rn, and that's like saying the linear transformation is onto. We already know that. Now we can reword that in terms of rank. We can say the rank of the matrix is n. The rank must be equal to n. Then also equivalent to that is the null space of the matrix being just the 0 vector. That's equivalent to saying the corresponding linear transformation is 1 to 1. And if the null space of A is just the 0 vector, the dimension of the null space of A is 0. So if any one of these is true, all the others are true. If any one is false, all the others are false. So for instance, if you know that the rank of a matrix is n, you know that the null space of the matrix consists of just the 0 vector. And I guess for proof here, I'm going to just say, take a look at this on your own, because we're through.